Hi, this is Alex from devstories.eu. AlphaFold, Protein Structure Prediction, Episode 16 of 21. If an intermediate tensor is too massive for a single GPU, the standard instinct is to slice the model parameters across multiple cards. But when your neural network only has 93 million parameters and your activation tensors consume 20 gigabytes, slicing the model solves nothing. You need to slice the geometry of the data itself. That is exactly what dynamic axial parallelism resolves. To understand why this approach exists, we have to look at the bottlenecks identified in the FastFold paper. The core engine of AlphaFold is the evo-former block. It processes multiple sequence alignments and pair representations, which essentially function as massive two-dimensional grids of data. Standard tensor parallelism tries to handle heavy workloads by splitting the linear layer weights across different GPUs. For AlphaFold, this creates severe inefficiencies. Tensor parallelism requires frequent, heavy synchronization, triggering up to 12 communication steps per block. It also only applies to the attention and feed-forward modules. Worse, its scaling is hard-capped by the number of attention heads. In the AlphaFold pair stock, that limits you to a maximum of just 4 GPUs. Dynamic Axial Parallelism, or DAP, abandons the weight-splitting approach entirely. Instead, DAP keeps the complete model parameters intact on every single device. The model itself is never distributed. The intermediate activations are. The evo-former processes data along 2 sequence dimensions, but the mathematical operations only ever happen along 1 dimension at a time. This behavior allows DAP to cleanly divide the data along the inactive dimension. You can picture this in a multi-GPU setup. A massive grid of sequence data enters the layer. DAP slices this input horizontally. GPU 0 takes the first chunk of rows, GPU 1 takes the next, and so on. Each GPU then calculates the attention for its specific slice of data. Because every GPU holds a full copy of the model weights, and because the computation is isolated to the horizontal axis, the GPUs do not need to talk to each other. They compute their chunks independently. Here is the key insight. Once that horizontal calculation finishes, the model needs to process the data along the vertical sequence dimension. To make this happen, the GPUs execute an all-to-all communication step. They scatter the geometry of the data across the network. GPU 0 scatters its column fragments to the other devices and gathers the pieces it needs for the next phase. The orientation of the split flips. Now the data is sliced vertically across the cluster. The GPUs immediately run the next layer of attention calculations, again with 0 crosstalk during the actual math. This transposition strategy drops the communication volume by a full order of magnitude compared to standard tensor parallelism. It also enables parallelism across every single computational module in the evo-former. Because the massive activation tensors are evenly distributed across the cluster, overall memory consumption drops heavily, preventing individual devices from crashing under the weight of long sequences. When your hardware bottleneck is driven by the sheer physical size of intermediate representations rather than the depth of the neural network, you do not fragment the architecture. You distribute the axes of the data. That is all for this one. Thanks for listening, and keep building.